Hello, everyone. My name is Salvador Pineda, and I belong to the OASIS research group at the University of Malaga in Spain. Today, I'm going to present you a work I have been working on with my colleagues Juan Miguel Morales, also from the University of Malaga, and with Judith working from the New York University. And the title of our presentation is Learning-Based Coordination of Transmission and Distribution Operations. So let me just start by setting a little bit of the scene and talk about the coordination between transmission and distribution network in the old days. So basically, the transmission network is a mesh network, high voltage mesh network that is connected to usually radial low voltage distribution networks. So in the old days, the thing is that the old small consumers were inflexible, so they didn't really react to electricity prices. And somehow it was an advantage to operate the transmission power system, because the only thing you have to do is somehow predict the consumption of each distribution network and then treat it as just a fixed load in the connection point. And that was predicting the consumption of the distribution network was not very difficult, because every weekday at 5, so the demand is more or less the same. So it was kind of an easy task. And it was also good because then you could replace each distribution network by a fixed load, and you could operate the transmission network with relatively in a low computational time. And also you didn't need any kind of information exchange between distribution and transmission network. However, like in the present or in the future, you may argue a bit about when this is going to become a reality. So in the distribution network, we have more and more consumers that are flexible to electricity prices, right? So you may change your consumption depending on the price. And distribution network are also including more and more distributed energy resources, such as solar, for example. So now the behavior of this distribution network cannot be so easily predicted. And the question that we try to answer in this presentation is, well, how should we then operate the transmission network in this new paradigm? There are some answers in the literature, in the technical literature for this question, and we have split all methods in 2 different categories. In the first one, we have the exact methods. So, for example, the centralized. We'll talk a bit about each of these 3 methods, and then in a second group, we have the approximate method. So, for example, in the exact method, the most probably obvious way to address this problem is, okay, I'm just going to take a full representation of all the transmission and all distribution networks. And then I'm going to solve like an OPF kind of problem. Then you'll need all information about, for example, network topology of distribution networks that maybe not always available. You also need information about the behavior of the customers, and maybe that's also private information. So that's one of the disadvantages of this approach. And the second one is, even if you had access to all this information, solving the full model is going to be very expensive from a computational point of view. So in order to address, to avoid the disadvantages, we can apply decomposition methods, because there are only in this kind of situation, there are a few complicating variable of constraints, and then this is a very good problem to apply decomposition. Still, you're going to need access to all information, but at least your computational time is going to be decreased. And in the third place, we have decentralized approaches. These are iterative approaches, and in each iteration, you have some information going from the transmission network to the distribution network and back and forth. And the problem with this, you are also going to achieve some computational savings, but the problem is that these decentralized methods rely on having a very robust communication infrastructure. So if this communication fail or you have some delays, then there is a problem with this. This is the main disadvantage of decentralized method. So in the second group, we have approximate methods. So you're not going to get the exact optimal solution, but maybe a close enough one. So that's what we are going to discuss in this presentation. So one approximate method is we call it the single bus approach, and it consists in just disregarding all technical constraints of distribution network. So you don't consider like voltage limits or like network limits and so on. You assume that all consumers and distributed resources are just located in the connection point. So it's this single bus method is going to be very fast, but you know you are only going to get good results for uncongested distribution network. Obviously, if you have some voltage congestion or like network congestion, then this method is not going to provide very good results. Then the second approximate method, it assumes that the response of the distribution network is independent on the price, like similarly to the old days. So there might exist some flexibility, but we assume it's small enough so that we can just ignore it. So in this method, you just have is access to a lot of prices and consumption at the substations between the transmission and the distribution networks, and then you can use some kind of regression method or machine learning method so that for a new hour you can predict how much the distribution network is going to consume. Of course, this is only going to provide good results if you have passive distribution networks. If these distribution networks are reacting to prices, then things are going to go wrong. And in the last place, we have the method we propose, and it's a price-aware method. If you notice, so in the first method, this assume it disregards technical stuff with distribution network. The second one disregards like economic aspects of the behavior. And in this one, what we want to do is to take these both effects into account. The good thing about this method, as I'll explain in a minute, is that we don't require any information about the distribution network or the consumers, and we don't need any robust communication infrastructure either. We only need access to historical information at the substation about prices and quantities. And the method we propose can also depend on some contextual information. So how this method works is for each distribution network, we have access, as I said, to the response of the distribution network for each price at the substation. Then for a given context, we select the closest price response pairs. You can do that with some nearest neighbor method. For example, here in the afternoon, these are the points recorded in the afternoon, and this is during the night, for example. Then these points are approximated using a non-increasing stepwise function. So for example, in this case, this is just an illustrative example. We consider like C3 blocks. to represent the response of the distribution network. And finally, once you have done that for each distribution network, you replace each of them by this stepwise curve. Here they are all the same because I was lazy and I just copy paste the same figure, but they can be different. And then you operate the transmission network, assuming this response at each connection point. What we did in this work was to compare these three different approximation methods: the single bus, the price agnostic, and the price aware. Once these methods were used, we determined the electricity price at the substations according to each approximation, and then we submit these prices to the distribution network, and we solve the optimal operation of each distribution network assuming these prices. Of course, there is going to be some kind of mismatch between each of these methods of thought about the expected response of the distribution network at the actual response. So this is some kind of imbalance that you'll have to address using some kind of research, for example. So we are going to measure this mismatch, and we're also going to measure the social welfare loss caused by these different approximations. We compared the results in a case study that included one transmission network with 118 buses, in which we have a 91 distribution network with 32 buses connected to it. The distribution network included the flexible consumers using a linear reaction to price and some solar power units. What we realized when we were doing this research is that the results depending a lot on the congestion level of the distribution network, of course. So we change the parameters of the distribution network to change this important effect. We use the demand and the solar forecast in aggregated values as contextual information. And finally, we solved each approach with a training set including like 8,700 hours, and then we tested the results in an out of sample using 100 hours. And these are just the results. So what we have in this figure in the x-axis is a parameter just somehow tuning the congestion in the distribution network. So in the left side, we have low congested distribution network, in the right, high congested networks. And in the y-axis, we have the power imbalance as a percentage of the total demand. Since we tried this method for 100 hours, we have represented in this figure like the maximum mismatch, the minimum, and then the average for each of the three methods: the single bus, the price agnostic, and the price aware. That is the one we are proposing in this talk. So, well, it was not a surprise to us that if we have very low congested networks, then the single bus approximation is doing pretty well, and the power imbalance is almost zero. But if we have very high congestion, this method is doing very bad, and the price agnostic is doing much better. Why? Because if you have a very congested distribution network, like, prices don't matter that much, because I mean, if you need to keep your voltage between some limit, then the demand cannot really react to prices. So you have to set it to a point in which voltage limits are satisfied. And as you can see, the proposed method is not very affected by congestion, so more or less the results are stable, and the average imbalance is below 0.7% for in all cases. This figure is a similar one, but in the y-axis we have now the social welfare loss instead of the power imbalance. And this is in percentage with respect to the maximum social welfare you could have obtained using the full method. So as you can see, the maximum social welfare loss for the price agnostic or the single bus are around like 2–4%, depending on the congestion of the distribution network. However, in the proposed approach, the maximum social welfare loss is below 0.1% in all cases. So just to conclude this presentation, we have explained a bit the disadvantages of exact methods for TSO-DSO coordination, and these are that they require either a lot of information or they require a very robust communication infrastructure between TSO and DSO. And what we think it could be like a better way to or a more realistic way to address this issue is an approximation like learning-based approach that only requires measurements about quantities and prices at substations. So we don't depend on any communication infrastructure. We have then proposed a method to approximate this the response distribution network using a stepwise function that is non-increasing. And I forgot to mention that, but we did it this way because then this is, you don't need to really change the market clearing procedure, because that's like how everybody bids into the market, right? Using like blocks, bids or offers. And then our method also account for contextual information, so it can really adapt to day of the week or the day, etc. If we have compared our method to others approximation methods, ours reduce power imbalances that are below 0.7%, and also social welfare losses that are below 0.1%. So thank you very much for the attention. This is we have this work is under review, but you can find, if you're interested, you can download the preprint using this QR code. And if you have any question, I'll be happy to answer them. Thank you very much.